Hello guys, we're going to continue with chapter 15 and we have three more examples and we are going to be done with this chapter. Here we are still dealing with impulses and momentums, and we have block A falling on block B in this example, and we would like to find the distance that the spring is going to be compressed as a result of this collision between block A and B. They tell us that the coefficient of restitution between A and B is E, and we need to find the velocity of the big plate after this, and then we can find obviously the deflection of the spring after this whole thing. Okay, so how do we do this problem? So the way we're gonna solve this problem is by first throwing the momentum and impulses diagrams on each of the blocks. Well, what is the velocity of A just before the impact? Well, we know the velocity of A, right? I'm gonna call it VA1 before the impact, and by now we should all be familiar that it's gonna be equal to square root of 2gh, right? You can get that from bunch of ways that we've learned from acceleration. A is equal to g, and then integrate the acceleration and find the time when the distance is equal to h as a result of that, or you can use conservation of energy or whatever that you like. Okay, or mgh is equal to 1 over 2 mv squared, right? It will actually give you this. So I know block A is going to be falling with that speed before it hits block B. Now I need to do my momentum and impulses equations. So here's what I have. So before the impact, this is A, and then A is moving with what? With MA, right? VA1. And as a result of the impact, basically, this is again block A. And at the collision, basically, I'm going to actually have FDT, right? Which is the impulse applied on A during the impact, and then ultimately A might be going or may not be going with the same direction, but we're gonna keep it like that. We're gonna keep it in the same direction, and then if that number is negative, it means that block A will rebound. We don't know. Now, how about block B? So block B is originally at rest, right? So it wasn't moving, but then it sees an impulse from A, and that impulse is here, FDT. And as a result of this impulse, well, here's what. So we have an impulse of FDT coming in from block A, but then how about the spring? So the spring is actually also applying a force, right? Because here we're looking at the net force applied on the block during that instant of time. We have this block, and we actually have, well, we forgot about the weight too, right? So we actually have mg here, right? Mg dt, the weight coming downward, and then we have kx dt. So what I want to tell you guys is that kx dt, right? What is the force of the spring when the deflection is almost zero? Like when the impact occurred, basically are still near the equilibrium. What is the deflection at the equilibrium? Zero. So the spring actually does not create any impulse, and springs are non-impulsive. So you don't actually generate any impulse because of the spring. Why? Because when the impact occurred, basically the deflection on the spring is so small that when you multiply that by dt, it is actually zero, right? So k times deflection, which is very small, multiplied by dt, which is also a very small number. So spring cannot create any impulse. And likewise, the weight, so mg, the weight of this block multiplied by dt, is actually very small compared to the impulse that the block sees from that, right? So this is that would be in actual equilibrium. And even though like if this block is actually sitting here, then you don't even actually have mgt because you are already starting from the equilibrium, right? There is a force in the spring. That system is already in equilibrium. But here some people may argue that during the impact, how come I'm not considering mg? Because at the impact, if an object is falling down, if the distance is if the time is very large, basically, yes, you would need to add mg and then integrate it from time 0 to the final time. But if the time is very small, like let's say an object is falling down, right, and then when the object is falling, I give it some impact, right? So the velocity increase due to the impact is much greater than the velocity increase due to the weight during that impact duration. right? That is why we don't consider that. So when you want to take an object that is falling over a long time, then yes, but here you would have to integrate this FDDT, and then you would basically come back to our initial equations that we had. So here we don't have any mgdt, impulse due to gravity, or basically here we don't have any impulse due to gravity. Neither here we have any impulse due to the spring force. And here basically we're going to have our final velocity, which is going to be what? Or our final momentum, which is mb vb2. Alright, so let us continue this problem here on this white piece of paper. So basically this is what we have. So we know we have VA1, right? Let me write that. Is equal to square root of 2gh, and if you sum the impulses going downward, right, on block A, what do you get? If you do that, you are going to get on block A, you are going to get going downward. So this is my positive direction. Then I'm going to get MA VA1 minus FDT is equal to MA VA2. And then if you sum the impulses on block B, what do you get? You're going to get what? FDT in that case. FDT. So that FDT alone is going to give you MB VB2. So this is equation 1, and that is equation 2. And if I basically sum 1 and 2, I'm going to cancel FDT, right? So this is the very typical situation that we've been dealing with. So you're going to get MA VA1 is going to be equal to MA VA2 plus MB VB2. Alright, now the issue that we have here is basically we have two unknowns, right? So this is one equation, two unknowns. And for us to be able to solve VA1 and VB2, what do we have to use? We have to use the coefficient of restitution, right? And then we said the coefficient of restitution is VB2 minus VA2 divided by VA1 minus VB1. What is initial velocity of VB1? B has no initial velocity. How about block B, block A? Does it have a final velocity? Yes. Block A has an initial velocity. Yes. So we're gonna actually do this. So this and that. Basically, now we have two equations, two unknowns. If you consider that. So here we have two equations and then two unknowns. So therefore, VB2 minus VA2 is equal to E times VA1, and my goal is to find the goal of the problem is to find the velocity of the plate, so the velocity of B. So we need to find VB2, and we know VA1, right? So we know VA1, so we can replace VA2 then is equal to VB2 minus VA1. So take this guy and we're gonna plug it right there. You end up as what? MA VA1 is equal to MA VB2 minus E VA1 plus MB VB2, or MA VB2 minus MA E VA1 plus MB VB2, and this guy is MA VA1. Now I'm going to end up with MA VB2 is equal to MA VA1 MA, or I can factor out, right? MA VA1, or the whole thing, right? MA VA1 1 plus E, right? So if you move this to the other side, minus, right? So MA VB2 is equal to MA VA1 1 plus E minus MB VB2, and then divide this guy. Okay, no, so let me just, so we have actually VB2, we have two VB2. So VB2 MA plus MB, and then on this side you're going to have what? MA VA1 1 plus E. There you go. So VB2 is equal to VA1 1 plus E divided by, or MA divided by MA plus MB. Okay guys, so this is your answer, and what you have to remember here is basically the number of equations and number of unknowns, right? So we have, this is our equation that you get from the conservation of momentum. This is the equation that you get from the conservation of momentum for the two systems, and you use the coefficient of restitution along the line of impact, and from here basically you can find your final velocity. Okay guys, now this is example 8, and we have a person throwing a ball, 0.5 kilogram ball toward the wall with an initial velocity of 10 meters per second. We would like to find the velocity at which it strikes the wall. So we need to find basically this vector, and this is a projectile, by the way. This is not a straight line, right? Once you throw an object, as a result of gravity, an object will automatically take on a parabolic flight path. So we need to find the velocity at the wall, and then we need to find the velocity of the rebounding. So we need to find this velocity at B. So we need to find this, we're going to call this guy VB1, and then we're going to find VB2, the rebound velocity, and then they tell us that the coefficient of restitution at the wall is 0.5. We need to find this final distance that the ball basically travels back after the collision. And that's it. So how do we do this problem? We know this is VA, right? So the ball is thrown with this velocity. Let us see how we can find the time that it takes. So let's find this time T1. How do you find this time T1? Basically we know the distance, and then we know that the velocity in x direction is going to be constant. So we know that distance 3 is going to be equal to VA cosine 30 degree multiplied by T1, right? So time T1 is going to be equal to 3 divided by VA, which is 10 cosine 30. All right, so this is time. I'm not going to be computing the numbers. I'll let you guys do this. So T1 is going to be equal to 3 divided by VA cosine 30. Then we need to find the velocity. How do I know the velocity? Well, we know Vx will always be equal to VA cosine 30, but how about Vy? How do you find Vy? Well, we know Vy is going to be equal to what? VA sine 30 minus GT, because we have accelerations in a vertical direction, right? At time T1, then we're just gonna use that time T1, right? So here is how we can find Vx and Vy at the impact. All right, so now if here we have an impact, right? So we have an impact. So this is your wall, and then this is a ball, right? And the ball is coming with this velocity here, which is equal to, and I'm gonna call this guy the Vx is equal to VBx1, right? And then this guy is equal to VBy1. So this guy is VBx1, and then this guy is coming to the wall with the velocity of VBy1. So this guy is gonna come here, and then here it's gonna have an impact, right? And then the velocity is gonna, then the ball is gonna fly with a different velocity vector. So how do I know this velocity vector? How do I know the components of VB2? So this is VB2, and then this is VB1, right? Okay, so to do this, let us look a little bit into what is actually happening here, right? So the ball and this is the wall. So the ball is basically coming with this momentum, and as a result of the impulse with the wall, we know the impulse is going to be how? Like that, right? Because it takes a very short amount of time. There's no need to put the integration. And then the final moment, this is going to be equal to the final momentum, which is equal to that mvb2. Okay. We don't know FDT, so it's impossible for us to get FDT. Why? Because basically we're pushing on the wall, right? And in the case of momentums here, we don't know the mass of the wall or whatever the wall is connected to, which is in this case actually the ground, the whole earth, right? So here you're dealing about the impact of a ball and the earth. This is basically what is really happening. So we don't really know this value. What we will do, and in fact the earth actually does move as a result of a tiny ball hitting the earth, based on this purely theoretical physics, right? But we don't know the mass of the earth, and we don't know how much the earth will actually move. So we don't know this value of FDT, but what we do know is we know that there are no impulses in the y direction. So I know that if I sum the impulses in the y direction, I'm going to get what? mv vb1y is going to be equal to what? m vb2y, because they have the same mass. So the velocity in the y direction is actually equal, because we don't have any impulses. Nothing is pushing the ball as it hits a wall and then goes up. Unless there's friction, then the velocity, the upward velocity will be the same before and then after the impact. Alright, how about in the x direction? In the x direction, luckily they gave us the coefficient of restitution, so we're going to use this coefficient of restitution. How to use the coefficient of restitution here? We're going to say that we know E is going to be equal to what? So guys, the coefficient of restitution will always be applied along the line of impact, right? So this is your line of impact, right? And the coefficient of restitution applies along here. So what we are going to do is we're going to say that E is equal to VB2, B is the object which is Earth in this case, right? VB2 minus VA2, which is the wall, divided by VA1 minus VB1. We know the velocity of the Earth before and after the impact is going to be equal to this. Now here, remember, VA2 is assumed when you are using the coefficient of restitution. You assume that the final velocity of both is in the same direction as VA1. So here VA2 is actually equal to minus VA1, which makes sense, right? So the final velocity of the ball, right? By the way, here B is an object, right? So here the velocity of the ball, right, is going to be minus opposite to coefficient of restitution multiplied by VA1, right? Here A and B are two objects, right? A is the ball in this case, but here I labeled the velocity of the ball to VB1. So it doesn't really matter here. What you should know is, what you should understand from here is that when you hit the wall, basically you are going to be rebounding along the velocity along the line of impact is going to be equal to the opposite of VA1. All right, so this means that what we just solved for is what? So VB2x is equal to minus E VB1x. This is exactly what we mean by that. All right, guys. So now we have the final velocity of the ball after the impact. Now we are good, and now we are ready to find the final where the ball basically land. Right. So just to put that in context again. So this is the wall. That is the ball. The ball was coming with this velocity VB1, which had VB1x that we knew, and then it had VB1y, and then the ball basically hit this guy, and now it's going to be going with VB2, right? But what is the VB2y, right? The vertical component is going to be equal to VB1y, right? And VB2x is going to be equal to minus. So since I put the value here, right, I put the direction of the vector, it will be simply equal to what? E multiplied by VB1x, right? So VB2x in that direction is going to be equal to that. So how about the angle? So if I want to actually get the angle alpha, then I know that tangent alpha is going to be equal opposite divided by the adjacent, so it's going to be equal to VB1y divided by VB2x, right? Which is equal to E VB1x, which is what? VB2y divided by VB2x. Does it make sense, guys? So this is how you can find the rebounding angle of the ball with respect to this horizontal line. Alright, so alpha is going to be inverse tangent of VB1y divided by E VB1x. Alright, next step is we need to find the distance that the ball will travel from B to hit the ground. We know that the velocity, total velocity at B is going to be equal to square root of VB2x squared plus VB2y squared, and we said the angle is going to be tangent alpha, which is going to be equal to VB2y divided by VB2x. Remember, when you are doing the inverse of an angle, like these two have to be positive, and here you already know that the angle here is alpha, and this is VB2, and then that is the wall. So alpha is going to be equal to the, like you just mentioned, inverse tangent of VB2y divided by VB2x. So now basically you are back at projectile motion, and then you have a point that has some h, the elevation height, and we are trying to find the distance that the projectile will basically travel. I hope you guys are able to actually do this. Well, how do we know the distance h? Well, to know h, basically, well, we know this distance from here to here is 1.5, and we still need to know the small h, right? The small h is the elevation from A to this point. How do you know that small h? I think we know small h, which is equal to minus gt t1 over 2 square, right? Plus what? Plus va, the initial velocity. So here we're simply trying to find the elevation that ball A will basically have as a result of this velocity, this angle, and that we know the time t1 plus va sine 30 multiplied by t1. So we know this guy, and then we also know the time. It's just equal to 3 divided by 10 cosine 30. So we fully know small h, then total h is equal to 1.5 plus small h, so we know the height. What we are left to do is we can develop a new frame here, and then we can call this guy, like, you know, x1 and then y1, right? And then we know that y1 is going to be equal to minus g t squared over 2 plus VB2 sine alpha. VB2 sine alpha is going to be actually equal to what? Y1 is equal to minus gt squared over 2 plus what? Plus VB2y sine theta, which is equal to VB2y, right? Times t. Okay, so this this y as a function of time describe the position of the ball after the impact, and then it until this point. All right, so this is gonna be, so that is gonna be equal to what? It will be actually equal to minus 1.5 plus h. What remains here is to solve for t. So we're gonna solve for this tf. That will give me this time, the time when the ball basically is at minus large h. Alright, so we're gonna end up with g tf squared over 2 minus VB2y tf minus 1.5 plus h is equal to 0. So this is a quadratic equation that you can solve. And you are going to have two roots. The reason why you are going to have two roots is when you are solving this problem, basically the math thinks that t is, for example, your x-axis, right? So here you are solving for time here, right? As it goes through. So this is your launch velocity. So when is it possible for you to reach that point? So it's parabola, right? So you might reach it here, or you might reach it at minus time, whatever, right? So here basically you can solve TF from here, and once you obtain TF, you plug it where? You plug it in S. So S is going to be your X right now, which is equal to VB2X time T times TF, which you have solved from here. So this is going to be your final position. Alright guys, please solve this problem on your own, and make sure you are very confident in solving this problem on your own. And there are several problems in the assignments that actually look exactly like this, so make sure you are very familiar in solving them and getting the right answers based on the theories and methodology that I'm teaching you guys in this course.